Did you rewatch the video, Terrell?
What was that?
Did you rewatch the video?
Nah, not had the energy to do it. What the fuck is chasing me?
My dad was looking at me weird about my wallet since he never seen it in person.
Who?
My dad. Apparently, I just have like a weird virtual background. I'll turn it off today. I gotta switch it out on Monday anyway. Apparently, this wallet's apparently really weird. Everything I needed, one small place. I know when I got it, my mom was like, "You're gonna lose that." I said, "If I haven't lost my headphones that are very, very small, I'm not gonna lose that." See, my issue is I lose like big stuff. Like I lost a hoodie at one point. I went nuts. Are you playing Mario?
Yeah. Such a huge delay in this thing.
You know, the game needs a software update. There's such a giant amount of input lag. And it wouldn't be doing that if they actually remastered the game instead of just emulating it.
Okay, almost time to start. Oh wait, I found some stuff that I think you might want to start reading. I'll send that to you this weekend for
Yeah,
this.
that's great.
Yeah. No, the stuff you said you were interested in turned out to be fruitful, and I think there's some stuff that we can start with.
It's great to hear.
Okay. So last time we were talking about this problem with these interconnected tanks. Where we had these three tanks. And each one was 1,000 liters. And let's see, we started off our initial conditions. Was that the concentration of salt in tanks 1 at time 0, what was it, 50 grams per liter, and the concentration in tank 2 at time 0 is the same as the concentration of tank 3 at time 0, 0 grams per liter. And what happens in a 1 minute period, we do in the following order. We flush 100 gallons from tank 3. Or 100 liters, I should say. We flush 100 liters from tank 2 to tank 3. We flush 100 liters from tank 1 to tank 2. We put 100 liters of fresh water into tank 1. And we mix all tanks. So this little mixer in each tank that makes sure each tank is nice and homogeneous. And we want to know what happens over time. So it could be convenient to work in terms of concentrations. It could be convenient to work in terms of mass. It's up to you. So if we say M of IT is the mass of salt in tank I at time t, then say in grams, then M of IT is just going to be the concentration times 1,000. 1,000 liters times the concentration of salt in tank I times T. If I just take, if there's like 50 grams per liter and I multiply that by 1,000, I end up with 50,000 grams. That's how much salt is in that tank at time T. So you can go back and forth between, so M equals 1,000 times C, or the concentration equals the mass divided by 1,000. They're practically the same. I mean, just you multiply or divide by 1,000. And I asked you to come up with propagation equations. So we had, tank 1, tank 2, tank 3. We start off with 50 grams per liter here, 0 here, 0 here. And you can sort of put 0 coming in from the previous if we were putting this into an Excel spreadsheet. And I want you to come up with propagation equations. Then starting with tank 3, where the amount of salt in tank 3 is going to basically be the amount of salt in tank. So the amount of salt in tank 3 at time t plus 1. Let me just, there's some space on the board. Some of you had worked this out during class last time. Presumably some of you were still thinking about it. So Grams of salt. Let me say mass of salt. In tank 3 at time t plus 1 equals, and this is what we were talking about when we were talking about traffic. It's the mass of salt in tank 3 at time t plus the amount that enters between time t and time t plus 1 minus the amount that leaves. I keep saying amount, but I should be more specific. Mass that enters minus mass that leaves.
I thought we were solving for concentration.
We are, but going back and forth between mass and concentration is just a matter of going between, multiplying or dividing by 1,000. So we'll go back to concentration when we write over here.
Okay.
I think it might be easier to think in terms of mass. So the mass in tank 3 at time t plus 1 is going to be the mass in tank 3 at time t plus the amount that enters. So we have 100 liters entering from tank 2, and each one of those liters has the concentration from tank 2. So that this is just going to be plus 100 liters entering from tank 2 times the concentration from tank 2. So concentration from tank 2 is just going to be C2T. So we have 100 liters. Each one of those liters has a certain concentration, a certain number of grams per liter. That's how much mass is entering from tank 2. And the amount that leaves, we have 100 liters leaving from tank 3, so everything's moving in this direction. We have 100 liters leaving from tank 3. Every one of those liters has the concentration that tank 3 had at time t. So 100 times C of 3t. So the mass of salt in tank 3 at time t plus 1 equals the amount that was there at time t plus the amount that enters, 100 liters times the concentration of salt in tank 2 at time t. Oops, that should be minus the amount that leaves. So sorry, if I had a plus sign here before, that should be a minus 100 times the concentration of salt in tank 3 at time t. And now if I divide by 1,000 on both sides, we know that to go from mass to concentration, just divide by 1,000. So I'll put all this over 1,000. We end up with the concentration in tank 3 at time t equals the mass in tank 3 over 1,000. That's just the concentration in tank 3 at time t. These are already in terms of concentrations, but 100 over 1,000 is 0.1 plus 0.1 concentration in tank 2 at time t. And already in terms of concentration, 100 over 1,000 is 0.1 minus 0.1 concentration in tank 3 at time t. So basically, it's just what I wrote before. The amount, now we're talking concentration in tank 3 at time t is the stuff at time, sorry, this should be t plus 1. T3 plus 1. The concentration of salt in tank 3 at time t plus 1 is the concentration of salt in tank 3 at time t plus 0.1 times the amount, basically the amount that enters minus the amount that leaves. And we can simplify this a little bit. We have a C of 3t here and a C of 3t here. So we can write this as 0.9 C of 3t plus 0.1 C of 3t. So that's the concentration of salt in tank 3 at time t plus 1. And again, this came from the amount that was there to begin with, plus the amount that enters, minus the amount that leaves. We found that useful over and over again. Similarly, we can work out the concentration in tank 2 at time t plus 1. The concentration in tank 2 at time t plus 1 is the amount that was already there, C of 2t, plus the amount that enters, plus C, times 0.1 C of 1t, minus the amount that leaves, minus 0.1 C of 2t. And we can simplify this too. C 2t plus 1 equals, we take this and subtract off that, we get 0.9 C of 2t plus 0.1 C of 1t. And we can work out what the concentration is in tank 1. See, in tank 1 at time t plus 1. This time when we work it out, we're just adding 0. So we're just going to have 0.9 C 1t plus 0. So we have our 3 propagation formulas here for tank 1, tank 2, and tank 3. Simplify about as much as we can. And several of you ran this last time. I'm just going to do it for you now. So let's put all this stuff in. How about I put time in this column. Just drag that down a ways. That's fine. And I'm going to put a column of zeros. over here. Because we're flushing with fresh water, so let's put a bunch of zeros there. And so here's tank 1, and here's tank 2, here's tank 3. And initially, we'll do this in terms of concentration. We had 50 grams per liter here. We had 0 grams per liter here. We had 0 grams per liter here. And in tank 1, let's see, it was 0.9 times previous time period. So that's C2 plus 0, if you like. But I guess I don't need to do that. So I don't know why I put those zeros there. And in tank 2, we have, let's see, 0.9 times D2 plus 0.1 times C2. Oops, I forgot my equal sign. You ever do that? And over here I have I forgot my equal sign again, equals 0.9 times E2 plus 0.1 times D2. Let me put these all in. Just look at the coefficients in turn over here in tank 2 and tank 3. So you can see that the concentration in tank 2 at time t plus 1 depends on D2 and C2. In other words, the concentration in tanks 1 and tank 2. And there are coefficients in front, 0.9 and 0.1. They add up to 1. Right? 0.9 and 0.1 add up to 1. And over here, they add up to 1 also. 0.9 plus 0.1 add up to 1. But over here, they don't. I just have 0.9. And so they don't all add up to 1 everywhere. So what does that sort of tell you about the amount of salt in the system over time?
It's slowly decreasing.
Yeah, it's going to be decreasing slowly over time. There's salt disappearing. I mean, salt is leaving tank 3, and as far as we're concerned, it disappears into the ether. Okay, so let's drag this down and see what happens. Oh, several of you reasoned this out last time. Some of you, oops, right. Some of you saw it happen as you did this yourselves. Just drag this down. Doesn't matter how far you go exactly. I think we'll have a pretty good idea what's going on here. That looks like it's more than far enough. So you can see, of course, the amount of salt in tank 1 is dropping off. What we have here, of course, 0.9 times the previous time period. This is just exponential decay. And you can see that we have in tank 2 the amount of salt increasing for a while, because we started off with 0, and we have salt coming in from tank 1. So 5, 9, 12, 14, 16, 17, 18, 19.1, 19.37, 19.37, 102, 19.37, 102. And then it starts dropping off. And over here, it starts going up for a while, 0, 0.5, 1.35, 6, 7, 8, 9, 10, 11, 12, 0.2, 12.8, 13.3, 13.7, 14.0, 14.17, 14.25, 14.25, and then it starts dropping off, which is exactly what you told me last time. You can see that it starts dropping off in tank 2 before it starts dropping off in tank 3. It's already going down by let's see, by time period 13 here. And over here, it doesn't start going down until we get to like time period 21 or 22. Well, that makes sense. It's taking the salt some time to move through the system from tank 1, tank 2, tank 3, and it peaks earlier in tank 2 than it does in tank 3. You can also see, look over here when it's basically not going up and going down. You can see that what happened is there's exactly, in time period 9, there's basically exactly as much salt. The concentration in tank 1 is pretty much the same as the concentration of salt in tank 2. And so, of course, the amount of salt between time 9 and time 10 is neither going up nor down. Because if I'm just flushing some saline solution out here in tank 3, and I'm flushing solution in from tank 1 that's exactly the same concentration, the salinity is neither going to go up nor down. So these numbers should all tell you a story. The coefficients, 0.9 and 0.1, they should tell you a story too. This should all make intuitive sense. This should be an intuitive process. So how do you feel about this so far? Is this okay? We've been doing the same sort of thing over and over again with different different applications. Heat. I have another one for you coming up, but here we have tanks. We had what else did we do? Traffic. We're dividing space up into discrete parts. In this case, we just divide space up into 3 discrete parts. We divide that bar up into discrete parts. It makes total sense to divide tanks up into 3 parts because there are 3 tanks. Whether or not it makes sense to divide a bar up into 9 parts or 11 parts or however many parts you're dividing it into, that's up to you. That's sort of an artificial thing. With the road, it doesn't necessarily make sense to divide it into 1 mile intervals. That's kind of an artificial thing. And we're also dividing time up into discrete parts. So I'm almost trying to make you sick of this discrete space, discrete time stuff. Oh, let me stop screen sharing. Let me just give you one more application right now of discrete space and discrete time. And we'll just start this. How about infection propagation? Let's say, for the sake of argument, we were in the middle of a pandemic. And we wanted to know how infection was propagating. Let's do this in 2 dimensions. That way we can sort of draw a map. So we'll make this the x direction. And this will be like the y direction. And we'll keep t discrete. So x and y and t will again be discrete. So we're breaking this up into cells, and we'll keep time 0, time 1, time 2, and so on. Let's just focus on a single cell. So we're at position x, comma, y. And so focus on one cell at a particular time. Insofar as disease propagation goes, and I'm about to make an assumption, assuming you can only catch the disease once, assuming you can only catch the disease once, and afterwards you're immune, there are, in one cell at a particular time period, there are 3 distinct populations. What are they? What are the 3 populations at a particular time in a particular area that we care about in terms of disease propagation?
The rate in which people catch the disease, the rate in the time where they stay sick, and when they, like, the disease leaves, like the rate of people who heal, and the rate of people who get worse.
Okay, that you answered. You gave me a correct answer to a question that I didn't ask. What you told me are parameters, and those are important. But you've already jumped into the next step. So how you're talking about how contagious the disease is, how infectious it is. You know, certain diseases, some are more infectious than others. The length of time that somebody might be infected. These are all important parameters, but we're not there yet, and I don't even know if we're going to get that far. I just want to talk about the 3 distinct populations. How would you divide people up in terms of disease propagation? Yes, Kevin.
Should we do age?
Oh, that's okay. Now I see where you're going with this. You're talking about susceptibility. That, say, in terms of coronavirus, some age groups tend to be more susceptible. I'm looking for something way more basic.
The amount of people who stay home.
Again, you're talking about transmissibility. I'm talking about all sort of infectious diseases. I think maybe
Proximity?
you're all jumping to the hard part.
Individuals who haven't gotten the virus, individuals who are, I was saying individuals who haven't gotten it, individuals who are currently sick, and individuals who are immune.
Right, exactly. The 3 distinct populations are people who haven't caught it yet. They're the susceptible ones. People who have it now, they're the ones you want to stay away from, right? And people who already had it, they're the people who are presumably safe. So, what do we want to call it? S for susceptible. S of X, Y. So we're in cell X, Y at time T. So this is the number of susceptible people. The number of people who haven't caught it yet. Let's see if I use I. Yeah, I'll use I for infectious. So I like everything you were saying before, but you would jump several steps into the future. And let's say R, these are the number of people who've recovered already. Presumably they're immune. So these could be, I wrote number, these could be like percentages of infectious people, percentages of infected people, percentages of recovered people. But no matter what, as long as you can only catch a disease once, you basically have these three populations, no matter what the characteristics of the disease are. Now, what does transmissibility have to do with? How does somebody, get the disease? In terms of these populations.
They would have to be close to the people who are infected. So
Who does?
And
The
member
people
of
who are
I
at
is
risk.
equal to a member of S.
Exactly. So disease is transmitted when we have contact between a susceptible person and an infected person, right? These people don't even come into it. So the disease is transmitted when you have contact between a susceptible person and an infected person. Whatever that contact is, it has to be closer for some diseases than for other diseases. And so if we were going to build such a model in sort of this two-dimensional environment, by the way, this is kind of how it works. This is kind of how we build these models. In each one of these X, Y, you'd have your number of susceptible people, your number of infected people, and your number of recovered people at a particular time. Maybe there's an outbreak in this cell right here, and you want to figure out what happens over time. Obviously, the susceptible people in this cell are going to, the infected people in this cell are going to affect the susceptible people in this cell, but the infected people in this cell, assuming there's some travel, are going to infect the susceptible people in neighboring cells. Now the question becomes much more complicated. How much are people traveling? Do people over here affect the people over here? Do people over here affect the people over there? And it becomes this very complicated model because it depends on so many things, not only factors about the disease, but how people are mobile. How mobile are people? And of course, people get on airplanes, and this cell over here suddenly affects that cell, in the next country. But this is how it works. And one more point I wanted to make about this kind of model. Oh yeah. So in the early days of COVID, I don't know if you remember this from last spring, seems like so long ago. In the early days of COVID, we saw basically locally and nationally exponential growth. We saw exponential growth basically because the number of susceptible people determined at that point basically how many new infectious cases there were, and the number of the number of susceptible people was increasing exponentially. Eventually, and we didn't let it get this far. We started social distancing. We started wearing masks. We never let it grow uncontrolled. If we had the situation, I mean, we've had what, about 200,000 deaths. We would have had easily 10 times that number if we had just let it grow uncontrolled. But how do we let it grow uncontrolled? And there are certain diseases that are not so serious that we let grow uncontrolled. The number of infected people continues to grow for a while. The number of susceptible people eventually starts to shrink, right? Either everybody has it or everybody had it. And so when the number of susceptible people eventually starts to shrink, we are going to end up with something that looks like that. We couldn't let that happen with COVID because too many people would have died. But eventually, exponential growth, as always, can't keep up forever. It doesn't go on forever. Eventually, the number of susceptible people starts to shrink, and so the number of contacts between susceptible people and infected people is going to shrink because the number of susceptible people is shrinking. Again, we couldn't let that happen. If we had, it would have been much, much worse than it is. But there we go. Anyway, I wanted to introduce this. We could build such a model, just like we've been doing, except in every cell, we wouldn't just have one thing we're talking about. We'd have three: number of susceptible people, the number of infected people, the number of recovered people. If anybody is interested in this kind of thing for their final project, feel free to talk to me about it. We can try to put some sort of model together. I've had students before that have built atmospheric models where we build sort of a map, and in each map, we put like a pressure and a, let's see, we had pressure and I guess wind velocity and maybe one or two more things. We don't want it to get too complicated. And you can see what happens over time. This air sort of leaks in this direction, and we can see what's happening. I had a student years ago who wanted to take a look at hurricane formation using Coriolis. Now, that was it was a funny one, because when we built when she built the model the first time, and I helped her with it, we forgot that we needed some place for air to disappear to. So what happens, of course, when you have hurricanes growing is you have these warm spots over the ocean, and you have the air warming up above those spots, and the air rises. And at the lower level, it basically disappears because it disappears into the upper atmosphere. We forgot that the air needed some place to go. So she had this low pressure system right in the middle, and she had the air coming in, and we had built the Coriolis into it. And as the air came in, it started to spin, which was great. But then the pressure, since we had no place for the air to go, the pressure started rising in the middle. And so it started coming out again, and it started spinning the other direction. So it just kept coming in and going out and coming in and going out like a heartbeat almost, and which is definitely not what we wanted. But it was very interesting that we had made this. I don't know why it didn't occur to us. It just didn't. It was very interesting to see what our mistake led to in terms of behavior. What I would like to start segueing to is talking a little bit about continuous space and or continuous time. And you'll see why I don't want to spend too much time on this. This is the realm of differential equations. The reason I don't want to spend too much time on this is not because I don't think you can handle differential equations. Some of you have taken a course in differential equations. And all of you have taken calculus. So you all have enough background to understand what differential equations are all about. But we have another course in differential equations. I don't want to turn this into a course in differential equations. But to make what we've talked about so far sort of make sense generally, I do want to talk about differential equations and compare what are called difference equations, which is what we've been talking about, with differential equations, so you can compare and contrast them. And we'll take a look at some of the same kinds of situations from a continuous standpoint, and you can see how they work. But anyway, that's where I want to start segueing as of next week. Seems like we finished a little early today. Does anybody object? Do you feel shortchanged if I let you go 6 minutes early? No? Are you sure? Okay, good, because no refunds on this lecture. All right. I will see you all on Monday. Have a great weekend.
You too.
Thank you.